Hello and welcome to our video on multi-resolution data fusion for super-resolution electron microscopy, which we designed for electron microscopists to be able to study structures of atoms, virus behavior, mutation in DNA, or long-range cracks in materials. And typically, the choice of device to study these properties is a high-resolution electron microscope, which can be operated in one of two modes. The first is a high-resolution scanning mode, which gives us detailed image information, but typically this is at the cost of time because it's pretty slow. Or we can save time by low-resolution scanning and get an image like this, which is not very informative. In fact, the central challenge is that all electron microscopy data imaged to date represents less than 1 cubic millimeter. Think about it. So, how can we acquire data faster without compromising on image resolution and quality? Here's a thought. Why don't we take a high-resolution scan over a very small field of view and a low-resolution scan over the entire image and fuse them to get a uniformly high-resolution image, bringing us to multi-resolution data fusion, or MDF. We begin MDF by acquiring a high-resolution library of typical structures, like this and this, and a low-resolution scan, which is scanned really fast over the full field of view, and then we combine them to form a beautiful image that's high-resolution. But surely, someone must have worked on this before. In fact, there are algorithms, an example of which is Technion's single image super resolution, and we can apply it to electron microscopy, but it produces an image like this one, which is not super informative. So how do we do it? The answer lies in Bayesian inversion. And we start out with a model for the microscope, which is also called a forward model, and our belief about the image, called a prior model, which is a probabilistic model. We then perform regularized inversion on both these models. So how do we form the prior model for MDF? Here are some considerations. A good model must be able to exploit the structural repetition in microscope images. And also, we must be able to induce high-resolution texture to the low-resolution images. Which brings us to library-based non-local means denoiser. Now, as a quick recap, in conventional non-local means denoising, we have an image that we want to denoise, and let's look at a single pixel and take a patch around it. So we go on in the image looking for similar patches, like the patch that we're trying to match, and then we weight each of these patches based on how similar they are and take a weighted mean to reproduce the patch. Instead of using low-resolution patches from the image, why not use a high-resolution patch library? This is the central idea of library-based non-local means. But how do we use it as a Bayesian prior model? The answer lies in a powerful framework called plug and play, and we start off with an initial reconstruction, which doesn't have to be too good. It's an initial guess, and we feed it into the forward model. The result of the forward model is then fed into another block, the prior model block, which is basically our library-based non-local means denoiser. This is the strength of plug and play, in fact, that we can use a denoiser, and then we iterate in a loop until we hit convergence to produce these images. It worked so well that we wanted to push it to 16x super resolution. And the low-resolution image on the left was acquired 228 times faster than it would take to acquire a high-resolution image. And our MDF algorithm still works really good. So this results in a 228x data acquisition speedup. But what about datasets with no regular structures, like this example? Even in this example, we see that our MDF algorithm performs much better than Technion's SISR or cubic interpolation because we don't have jaggies or other artifacts. And we are really excited about this, and we want to explore how much we can go further with this. Thank you for your attention.